DE number 3 is from the 2019 exam. It was question number 4, and you can see by this mean score that it was a difficult question. And its difficulty is not just in the differential equation portion, but there's a lot of related rates that are going on in this question. So I have this cylindrical barrel here, and it's collecting rainwater, and the rate of change of the height is given by this function here, dH dt, so that's the rate of change of the height. We're also told that the diameter of this barrel is 2 feet, and as this rainwater is collecting, that diameter does not change, so we have a constant radius of 1. Part A asks for the rate of change of the volume when the height is 4 feet, and we are given that volume formula right here, so I have to find dH dt. Before I do that, I'm going to simplify my volume formula. If my radius is constantly 1, that means I can replace the radius with the 1, and I can simplify that volume formula before I do the derivative. I'm going to do this derivative with respect to t. So derivative of volume with respect to t is just dv dt. The derivative of pi h is just the pi. But since I have a variable h here, and I'm doing the derivative with respect to the variable t, there's that implicit portion of this that I have to multiply times dH dt. This correct dV dt earns you the first point. And now I'm going to go back to my problem up here, and I have a definition of dH dt that I'm going to substitute in for my dH dt in my equation. And that gives me this dV dt equals pi times -1/10 square root of h. And I'm interested in the rate of change of the volume, that's dV dt, when my height is 4 feet. So now all I have to do is replace this h with a 4. And I'm using my evaluation notation, so dV dt evaluated at h equals 4. Just replace the h with a 4, and I come up with -pi/5. And it said also to indicate units of measure. This is rate of change of the volume, so I need a volume unit over a time unit. So my units are cubic feet per second. And that answer is worth a second point in part A. In part B, it says when the height of the water is 3 feet, is the rate of change of the height increasing or decreasing? The rate of change of the height, and you have this in the stem of the problem, is that dH dt. The way we tell if something is increasing or decreasing is we look to its derivative to see if it's positive or negative. So I need to find the derivative of dH dt at a height of 3 and see if I get a positive or negative, and that will tell me if that rate is increasing or decreasing. So let's start with our dH dt function, and we're going to do the derivative of it with respect to time. So here is my second derivative coming along down here. So I'm going to use a power rule. Bring down the power, so I'm going to bring down the power, that's the -1/20, and subtract 1 from the power, that's why the power becomes a -1/2, but since my variable is in h, and I'm doing this derivative with respect to the variable t, I have that added implicit step of multiplying times dH dt. You earn a point for this step in the second derivative, and a point to write dH dt, showing that you did that implicit differentiation. So now I need to replace this dH dt. I have what it's defined as right up here. So all I'm going to do is slip that -1/10 h to the 1/2 in the place of the dH dt. And my square root of h's are going to cancel out, and that just leaves me with 1/200. My second derivative is a constant 1/200. That is a positive value. So since my second derivative is positive, the rate of change of the height is increasing. I think part C will feel more familiar to you. So this is saying to use separation of variables to find an expression h in terms of t, and I have an initial condition when t equals 0, the height of the water, that h is 5. So I'm going to start with my dH dt, and I'm going to go through that process of separate the variables, integrate, solve for c, and then solve for h in this case. The separation of this is very important. If you can't separate, then a lot of times you are just out of the ball game when it comes to these questions. So the first thing I'm going to do is take my dt and multiply it through the equation. So that's designating the left side for my h's and the right side for my t's. And when I look at it like that, I can see that my h is out of place. So now I'm going to divide by h. And that separation is going to earn you a point. Next come my antiderivatives. I'm going to rewrite that 1 over the square root of h with the negative exponent before I do that antiderivative. So both of these are just power rules. So on the h to the negative 1/2, I'm going to add 1 to the power and divide by the new power. And the negative 1 over 10, the antiderivative is just negative 1 over 10t. Don't forget about your plus c that comes along when you do those antiderivatives. Point-wise, you earn 1 point for both of these antiderivatives to be correct. If you miss one of them, you just don't get the point. However, you're still in the running for subsequent points, so even if you know these are incorrect, just keep going. Our next move is going to be to solve for c. And I replace the h with my 5, and my t becomes a 0. And that gives me this value of c. Using that initial condition and writing the plus c is what this point is for. So even if you have incorrect antiderivatives, but you plug that initial condition into your incorrect antiderivatives, you are still eligible to receive this point over here. Let's pull our value of c into our equation. And our last move is just to solve for the h. So we're going to divide everybody by 2. And then square both sides to cancel out that square rooting. And that final equation for h is what your 9th point is. On these separation of variable problems, just keep that process in your head. You're going to see these variables sometimes switch from the x and the y that is our comfort zone to be different letters, but that process is the same. Separate the variables, integrate, write your plus c, solve for it, and then solve for whatever variable you're asked to solve for, in this case h.